Everyone, welcome to my presentation. My name is Franco Fusiyaboa and I'll be presenting my project title, Predictive Modeling of Diabetes Risk Using Health Behavior Indicators. Well, this work was completed as part of my clinical decision support modeling course, and the goal of this project is to explore how machine learning can predict diabetes risk using self-reported health behavior data. So diabetes affects more than 34 million Americans, which contributes significantly to healthcare costs and complications. And then the traditional screening often depends on the clinical measure of the average blood glucose level, which always miss behavioral and lifestyle factors that contribute strongly to patients who are at risk of diabetes. So these projects I used behavioral risk factor surveillance system from 2015 health behavior data to build an AI-driven clinical decision support model. My strongest, which is the key achievement, the strongest model was XGBoost, which achieved an ROC of 82 and 86% of accuracy, which outperformed logistic regression and random forest. So the problem I am addressing is that many individuals who are at risk of diabetes remain undiagnosed because current screening relies heavily on clinical tests, which always misses the behavioral predictors. So there is a need for an accurate, interpretable, and scalable model that uses self-reported behavior data. So this project develops a machine learning model on both balanced and then imbalanced data sets to improve early detection and support clinical decision making. With a literature review, existing studies shows that machine learning and explainable AI can improve early diabetes detection by incorporating behavioral and lifestyle indicators. Research also shows ensemble models like random forest and XGBoost perform strongly on health datasets, whilst SHAP explainability has been identified as essential for clinical trust. Well, these insights guided the choice of my models and evaluation methods used in this project. The datasets used, as I mentioned earlier, is behavioral risk factor surveillance, which is conducted every year by the CDC with over 400,000 responses. It contains information on health behavior, chronic conditions, and general lifestyle factors. And the two versions of datasets which I used were the balanced binary datasets and an imbalanced binary dataset. There was a third dataset, but I did not include it in this project. And the key features categories included clinical measures like the BMI and the blood measures, the blood pressure, behavioral factors such as smoking and physical activity, socioeconomic variables such as income and education, and general health status. Well, these factors have strong association with diabetes risk. With my exploratory analysis, I confirmed no missing values. The balanced data sets had a perfect 50-50 distribution, while the imbalanced data sets reflected a real-world majority of negative classes. Well, the key pattern, as I mentioned earlier, are where the higher BMI, poor general health, and high blood pressure and high cholesterol were all strongly associated with diabetes. And then behavioral factors like diet and smoking showed meaningful differences as well. So a correlation analysis showed a strong positive association between diabetes and BMI, high blood pressure, and high cholesterol, and negative association with physical activity. Yeah. So with my methodology, I started loading and then previewed the dataset for quality checks, cleaned and encoded features like features, and then I split the data into train and test sets where I did it by 80 and 20 percentage respectively. The trained models on balanced data, then extended. First of all, I trained the models on the balanced data and then extended it to the imbalanced data using the baseline models, and later applied SMOTE on the same test sets. The models included logistic regression, random forest, and XGBoost. And then I evaluated the models using accuracy, recall, F1 score, and ROC, and perform hyperparameter tuning using the grid search CV, and then used SHAP explainability to understand how each feature impacts the predictions. So on the results on the balanced data set, you realize it gave a baseline comparison across all the models. Logistic regression had a solid baseline performance. Random forest improved recall for the diabetes class, whereas XGBoost had the best overall AOC and an F1 score. Well, this results informed me that complex or more complex models will be able to capture nonlinear relationships even better. And then you realize the feature importance, both models which are the random forest and then the XGBoost agree that health related features like the BMI, general health, and then physical health are more important, and then the random forest spreads importance across more features, while XGBoost puts more weight on a few top predictors. Okay, so this slide compares the model's performance before and after applying SMOTE using the same imbalance test set. So what I want to do is I want to see how resampling affects each model's ability to detect diabetes cases, where SMOTE significantly improved the model's ability to identify diabetic cases, especially for logistic regression. And then accuracy and precision dropped slightly after SMOTE, and which was expected when recall increases. Random forest and XGBoost showed smaller improvements, but remained stable and still reliable. XGBoost still performed the best overall when balancing accuracy, recall, and an AUC. And then the feature importance, the top 10 feature importance, XGBoost model identifies blood pressure, cholesterol, diet, general health, and then lifestyle behaviors as the strongest predictors of diabetes risk. Now, when comparing the ROC curves, XGBoost had the highest AUC of 0.82, indicating the best ability to distinguish between diabetes and non-diabetes. And then logistic regression performed consistently with AUC of 0.81, whilst random forest scored slightly lower at a 0.815 due to overfitting of the SMOTE balanced data. So I did some hyperparameter tuning where I used grid search CV to tune parameters for all the models. And then the key outcomes were logistic regression improved through the regularization tuning. And then random forest achieved a very high cross-validation AUC of 97. And SGBoost also performed strongly with optimized boosting parameters. Yes, so now I use the SHAP visualization to explain how each feature influences the model's prediction of diabetes risk using the tuned SGBoost model. The two plots were which the bar plots show overall importance of each feature, and then the B-SWAN plot shows how high or low values of each feature push the prediction towards higher or lower diabetes risk. The red on the right, which indicates high feature values, increases diabetes risk, and then on the left, low, which is the blue, indicates low feature values, which reduces diabetes risk. So you realize the general health, high blood pressure, age, BMI, and high cholesterol have the strongest impact on the prediction. Now to my conclusion, the model effectively predicted diabetes risk using health behavior indicators. SGBoost provided the best real-world performance, whilst SHAP explainability validated the clinical relevance of the model's decision, supporting the development of transparent and interpretable decision support too. Now my future work is to test more advanced models like light GBM and other models, add more clinical and behavioral features for improved accuracy, and then validate predictions with clinicians and then real patient data. Thank you very much for watching my presentation.